you everyone for coming. Hope you're enjoying your beer, and it's great to have had Bianca talk before me. I don't know where she is, because she made an excellent introduction for this topic, because both of our research are actually very linked. So I bring to you this talk, which I call The Discovery of Hypervelocity Star. I'm Manuel Cavieres, and I've not worked on this alone. I've been supervised by Professor Lena Rossi and Sergei Kopesov, and Sefer, who's there in the public as well. So first I wanted to show you this view of the galaxy. If we were actually able to see our galaxy from outside, edge on, what we would see is something like this. This is actually the view that's reconstructed from the Gaia satellite, and I will tell you a bit more about it later. What you would see is this basically very narrow structure in which most of the stars of our Milky Way lie, and you can see that it's actually cluttered by a lot of dust. And what interstellar dust does is basically it's like smog. I don't know if you ever live in a city with a lot of smog, but you cannot see most of the city because of it. So it actually obscures most of the stars in our Milky Way. Here at Magellan and Clouds, my favorite galaxy as well. And if we were to zoom in into this region here, with an optical telescope here with the SDSS survey, what you would see is an image like this. So it doesn't look pretty remarkable, actually. So it kind of contrasts with what Bianca showed you of this region being like extremely dense and like full of stars, actually. But if you put on your near-infrared goggles, what you would see is a different image. So here I'm starting to overlay near-infrared data from the Spitzer telescope. And you can see that in the same image, and this is actually exactly the same field of view, it's actually full of stars. And in this region, which is in the constellation of Sagittarius, we have the center of our galaxy, and it's the most dense region that we actually are able to probe within our own Milky Way. And you can also see that even if we look through it in the near infrared, it's still full of dust. So we still have stripes that we cannot really measure. And this actually makes it very hard to study this region, because can you even identify a single star here? It's very hard. Even for an 8-meter telescope, it's going to be very hard to distinguish one star from the next. So this is what we call crowding. So we have two effects in the galactic center that makes it very hard to study. One is dust, and the other one is crowding. And you can deal a bit with crowding with a technique called interferometry. So you mix the data from different telescopes, and then if you, on top of your near-infrared goggles, you put your interferometry goggles. What you will see, if you zoom even farther into the center of this region, is what we call the nuclear star cluster. And you will see a collection of stars that are orbiting around a point of mass that seems to be empty. So they're just orbiting nothing. And this is actually the evidence that we have of the supermassive black hole in the center of our galaxy, Sagittarius A star. And using actually the trajectory of this star here in red, we learned that this supermassive black hole has 4 million solar masses. So we can use that trajectory itself to tell us about the acceleration, so we know about mass. So what I wanted to imagine here is if we are in this region, extremely dense, lots of stars, and you have a binary system, such as the ones that Bianca showed you in the Hills mechanism. We can have this binary in a parabolic orbit that's approaching our black hole, here signaled in white. And this binary is just going around, is doing its thing, and due to a number of mechanisms, it eventually arrives close enough to the black hole that it becomes disrupted. Once this happens, the tidal forces of the black hole tear the binary apart, and we have to zoom out, because one of these stars will be ejected at a fast velocity, while the other star becomes bound to the black hole. And this is the star that Bianca told you about, and in this talk, I will tell you about the other star that gets ejected at a velocity. So just to make everything like extremely clear, here, this is the hypervelocity star. So this mechanism will actually allow you to get stars ejected up to thousands of kilometers per second, or spoiler, maybe like a few hundreds as well. And it will also give you a capture star. And these are also called like A stars because this like very small cluster of stars around the black hole is called the A star cluster. And this is a lovely black hole in the center of our galaxy, Sagittarius A star. So a bit of context. When I got hired with the task of finding more hypervelocity stars, there was only one confirmed hypervelocity star by my co-supervisor, Sergei Kobosov, and he named it the S5 HBS1. Yes, we do have a problem in astronomy. And he found it by just looking for something else. He was studying these like extended structures in the outskirts of our galaxy, which are called stellar streams. And in his study to actually measure the velocity and the chemistry of these stars, he found one star with an abnormal velocity, thousands of kilometers per second. And he thought at first, okay, maybe my pipeline, my data is something wrong, maybe I'm doing things wrong, but it turned out to be correct. And if he traced back the orbit, it happened to have been ejected from the galactic center with a velocity of around 6 million kilometers an hour. So for context, this theory that the fastest man-made object is a manhole cover that was on top of a nuclear test that became ejected was like 66 kilometers an hour, at least a bit more. So, yeah, as I was telling you, about a year ago I got hired with the task of finding more hypervelocity stars. And this task has been more limited and limited because my predecessor was hired with the task of finding 100. They told me, can you even find one, please? So how do we actually find a hypervelocity star? So the main issue is that if we just look at a star in the sky, they're not very different from any other star. So we have kind of a few criteria. We wanted to move fast. We wanted to be hypervelocity. We wanted to come from the galactic center. So we actually need the star to come from an interaction with Sagittarius A star. And as I said before, this means that they're not very different from any other stars, so we're not looking for like red stars, stars in this part of the sky or this part of the sky, anything like that. And the other thing to keep in mind is that they're actually extremely rare. So we can expect current estimates to find 1 in 100 million stars in the galaxy will be a hypervelocity star. So we need a way to select stars that are super rare, that we don't really know what they are, that's very sensitive to this 1 in 100 million objects. So here's what we did. We took Gaia data, and Gaia is unequivocally the best telescope ever made for the astronomers in the audience. There's no discussion about this. And actually the images I've been showing you thus far are mostly reconstructed from Gaia data. And what Gaia does is it measures the position of stars very precisely. And precise enough that you can actually tell if the star is moving kind of up and down or left and right. It also gives you a rough estimate of the distance, but for this work we didn't use it. And the other thing we're missing from Gaia, for most of our stars, is how fast it's moving kind of in the direction of the line of sight. And the way we can get this is by combining Gaia data with data from the dark energy spectroscopic instrument. And you see here a field. It's actually every single thing here is an actuator with a fiber. So what this does is it captures spectra of about 5,000 stars in a single pointing. And a spectra is just if you grab the light of the star and you split it up in wavelength, what you're going to get is different lines of emission from the star are shown in your spectrum. And I'm going to have some trust in humanity and give you guys a very precious spectra to me, which is a photographic plate of a spectra. So you can like pass it around, you can see how a spectra looks like actually. And the way we used to do this for the last 100 years is that we would just point our telescope to a single star and get a single spectra. And the difference with this instrument is it allows us to get 5,000 spectra per pointing. So we can really start mapping the galaxy using this new generation of instruments that have only been working for the last few years. And actually, my job was to work with data from one of these instruments that they've been failing to get it to work for the last 15 years. So it's actually something very hard to do. Careful with it, please. So using these emission lines that we see in the spectra and absorption lines, actually, we can measure the line of sight velocity, and we can compare it with our models to also get a distance to the star. So combining this Gaia data that gives us the velocity like this and like this, with the velocity in the other direction from this spectra, and the distance, we can build a map of our galaxy that's actually in 6 dimensions. So you can see here every star that was probed with the dark energy spectroscopic instrument, mapped in the galaxy with its position, also from Gaia data. And what we did is then we took every star here, and we asked the question, does this star come from the galactic center? So given our best knowledge of the Milky Way, the mass distribution of it, what if we integrate the orbit backwards in time? Does this star come from the galactic center? And the way we did this is, for example, let's say this star, we know its position, but we don't know it extremely precisely. We have uncertainties. So we need to take into account these uncertainties. And what we do is we run this orbit 1,000 times, going over these uncertainties. So as we go over the uncertainties, we get different trajectories that are actually compatible with this orbit. And each trajectory is going to give us, within our galaxy, which is this circle here, if we were looking at the galaxy from above, a point from which within the galaxy the star comes from. And then we ask the question, so let's say we have 1,000 trajectories. How many of these come from this yellow dot here? And that's the basis of our method. We grab stars in the halo of the Milky Way, so very far, that actually kind of left the galaxy already. We trace them back 1,000 times, and then we say, how many of those 1,000 times come from this yellow dot? And then we combine with two more things. One, we ask, is it kind of fast? Is it fast enough to come from a black hole? That's kind of easy to do. And we also match it with the chemistry of the star. One second. It's for the throat. And if we do this, we actually got, out of the 4 million stars that we mapped initially with DESI and Gaia, that only a single star passes the criteria of being a hypervelocity star, which we named DESI 312. I also don't like that name. And it happens to actually be in a bound orbit, so it goes against the 5th question of the quiz, that a hypervelocity star needs to be in an unbound orbit to our galaxy. So for everyone who got that wrong, you got a pass from me. And here I want to show you an animation of the orbit that this star traces. And this is just one of the thousands of realizations that we did for this star. So you can see that it's a very particular orbit. It actually leaves our galaxy that you can see here represented by this ellipsoid. And the region that Bianca focused was this yellow one, and it comes back in. So the star is in a trajectory that kind of allows it to leave the plane of our galaxy, go beyond the dust that typically obscures studies of the galactic center, into regions where it's actually easier to study it, in which it's now currently in, actually. So it's actually a prime object that allows us to see the galactic center and study it, not only from its velocity, but also from the fact that it actually shares the chemistry of the place that it was formed in, which we believe to be the galactic center. We think it was ejected with a velocity of about 700 kilometers per second if it was ejected from the center itself. And this, for context, is on the order of 1 million kilometers an hour. And you can see here a top view of the orbit as well. It's a very eccentric trajectory that it has as it goes about the Milky Way. And within its lifetime, we actually allow about 32 orbits like this to take place. And here is again, so we have a velocity of about 1 million kilometers an hour. We have an orbit that comes from the galactic center. And this star actually happens to be very similar to our sun. It has the same mass as our sun. It has, we think, roughly a similar age as well. And this really allows us in the future to really work with this star, to really learn things about the galactic center. And this is the cool thing about hypervelocity stars. It's not only that they move fast, it's that they really let us study the galactic center of our own galaxy in a way that we usually never can do. Because they let us probe the galactic center without all the dust and without all the crowding. And so I'm going to finish with that. That hypervelocity stars allows us to study the hidden regions of our galaxy. And we have just found what I call the second confirmed candidate. And hopefully in the future, we will find the third one. Thank you.
Thank you, Manuel. All right, question time. Yes.
So, in these binary systems, why are not both stars orbiting the black hole at the end? Why they get separated each other?
So it can actually happen that the binary is not perturbed, that the tidal force is not enough to actually separate the binary, and then you actually would have the binary would continue in an orbit around the black hole. So it actually depends on how the impact parameter of the binary is respect to the black hole, the phase as well of the binary. So there's like a lot of different properties of the binary that will impact if it ends up being a hypervelocity star and a Cultuur star, or if hypervelocity star and one of them plunges. And I think if you really want to go into detail on this, the previous speaker she really, most of her research is on this, and she will tell you. Thank you.
Yeah, so in the beginning you were saying that these hypervelocity stars are the ones that are ejected.
Yes.
But this one you found is still bounded to the black hole. So this is like a third category?
So this star was ejected from the galactic center. So it's not really bound to the black hole, but it's still bound to the galaxy as a whole. So if we were to only consider the gravity of the black hole itself, it will leave completely. But
so it's not going around the black hole?
No, it's going around the entire galaxy. So this is considering the gravity of the black hole, all the stars in the disk, and the dark matter of the galaxy. So this is orders of magnitude higher than the mass of the black hole.
I guess you've studied the spectrum of this star quite well. Can you also see evidence in the spectrum that it was actually a binary star earlier?
No, that's actually very hard. Unless you have a system such as a contact binary, you're not going to have lots of evidence of binarity in the spectra. The other thing that you can have is when you have one of the stars being a very massive star, so you get a lot of dust that basically pollutes the atmosphere of the secondary star. But those are kind of unlikely scenarios. So typically it's very hard to say that this star was a binary. What we can say from the spectra is that the chemistry of the star actually matches very well with the chemistry of the galactic center. So we really have we're starting to construct now a lot of evidence in terms of the chemistry that this star was actually formed in the galactic center. But in terms of the binarity, that's a bit harder to do.
Do you think that these stars are so rare that we would only expect like 1 or 2 or 3 per galaxy, or do you think there's actually like a lot more that we just haven't been able to detect?
So our current estimates for the Milky Way are about 1 in 100 million stars at this. So we do actually expect maybe a few hundreds per galaxy, but not all of these are going to be detectable. Not all of them are going to be able to tell them apart from other stars. So we really do kind of expect to detect a handful of them.
I was wondering, what is the time scale of this animation?
So the time scale of this animation, here we show 32 passages, which is the maximum amount that is allowed within the lifetime of the star, which is about the lifetime of our own sun, so it's about 8 billion years. And each orbit is about 200 million. So it's a big percentage of the lifetime of the universe that I'm showing here. Yeah.
So I know that the mass of the galaxy is huge that the star is bound to, but is there a possibility, since it's so eccentric and going out of the galaxy, that some other thing of maybe high mass slows down the star or something?
Something to slow down the star? Actually, a possibility that we explored is that it actually was ejected or interacted with one of the satellite galaxies of the Milky Way. Because it can go far enough outside of the galaxy that it can interact with satellite galaxies of the Milky Way. And if it actually comes close enough to the center of this galaxy, it can become bound to one of them.
Oh, so like,
Or it can actually be maybe ejected from one of them and just lie in this orbit. So that's one of the off cases that we actually have to check. And as far as we know, it didn't. Yes.
So, if one does get like heated out of the galaxy, like unbound, what is the time scale that you can capture it? Like, does it go so quickly that the chances of you actually observing it are very low, or is it slow enough for a lifetime?
So, for example, with S5HVS1, it is unbound to the galaxy, so it will eventually leave the galaxy. I believe we have to integrate a few million years back in time to see it come from the galactic center. And then it mostly depends on the luminosity of the star, how far we're going to be able to see it. So if it is unbound to the galaxy, it's going to start breaking and breaking and breaking as it gets further and further and further, because the galaxy will still come back. So it mostly depends on how massive the star is. For example, the star I showed is about 1 star mass, so we would barely even detect it because we needed to be kind of close, and we're kind of lucky in this time because we are seeing it about relatively close by. But it's usually of the orders of hundreds of millions of years to leave the galaxy.
Can you do this? Could you do the same for other galaxies? Like look if there are stars in Andromeda, for example.
That's something I've been thinking about. The problem is that the data that we use from this telescope, Gaia, it struggles to measure the position of the stars in other galaxies precisely enough to actually tell if they're moving up and down or left and right with enough precision to actually trace it back. I think you can do in other galaxies is kind of switch it a bit around, kind of search for stars that are in places that they don't belong in. So if you see a very massive star outside the galaxy, where you think, okay, we don't form stars outside galaxies, that's weird. But we see this very massive star here, so there has to be some way for it to travel from a region in which it can be formed to the region in which it is now. So that's one approach that we can do in different galaxies, and it has not been successful yet.
Okay, we have one there for a while, sorry.
Yeah, I was wondering if you can trace back at what time the star was ejected and the line and correlated to the other star.
Oh, I killed the slides. Actually, we cannot do it really, because we see currently, and we selected actually, if it, with the first orbit it comes back to the galactic center, and we know that to be true. But then we don't really have any evidence that the ejection happened in the first time it went to the galactic center. Because if you actually look at the orbit of the star, and I think this visualization is pretty good, it actually comes back to the galactic center every single time. So in any of these passages, it could have been ejected. So within the lifetime of the star, we consider all of them to be compatible, and for every statistic that we do, we consider all of them. So if we are talking about ejection velocity, that's averaged over all the times it went through the center.
So I think you said at some point that these stars can get they can interact with, for example, the Magellan Cloud.
Yes.
So would it be useful to look at, for example, the metallicity of the stars there, and then look for stars that have metallicities that are different than the general sort of population, and that way, maybe postulate that they were found out? Is that possible?
Yes, that is possible. So she asked a question about the metallicity of the star, and that's one thing that we can measure from the spectra is the ratio between the iron and the hydrogen that the star has. And if a star has more or less of this, it means that it was formed kind of later or sooner in the history of the universe, or it also tells you where it came from. And it's actually true that even for this star, we use this measurement as a way of detecting stars that have anomalous metallicities for their region. So we use the metallicity as one of the traces. In our case, for the galactic center. But I also tried searching for hypervelocity stars in the Magellan clouds, and then you can just switch your chemistry. You do your selection to select stars that have consistent chemistry with the Magellan clouds. And that happens to be harder because the Magellan clouds have a chemistry that's very similar to just random stars around the galaxy. So it makes it very hard to use it as a reliable detection of hypervelocity stars. Person there?
Yeah.
No?
Yeah, it's a small question. Maybe related to the talk before, can Lisa help here to find another hypervelocity star and retrieve some of the information?
I think Lisa can help us in terms of the rate, because it can tell us how often this mechanism that ejects stars actually also captures stars, because these two things are intrinsically linked. But in terms of detection, I think no.
Yeah, I was just curious, very nice work. So, what do you find most challenging personally? So you have to build a conceptual framework, but day-to-day work, developing new numerical methods or ways of just storing the data, the raw data that you need to have. I don't know. So yeah,
I think what I found most challenging was, I mean, when I got hired to do this, they told me it was a high-risk thing, that I might not find anything. But then I realized that they've spent 12 years trying to find one and didn't find anything. So I found very challenging not to give up. And I think the main difference there was a lot of luck.
very nice.
All right, I think I saw a question there.
Go on then.
Yes, and then maybe a last one.
So you showed us early on the importance of infrared for looking into the center of the galaxy. But you also enthusiastically told us that Gaia was the best telescope. Now, one of the ideas I've heard floating around is that ESA should build an infrared version of Gaia.
For sure.
So do you think it would be useful for these things because you'd be able to trace them closer back to source, or not because you just actually prefer the volume of the large scale?
I mean, it would definitely be useful for this type of searches because the galaxy is a disk. And as a result of that, what we will get when we actually look at the trajectories of stars is that if you eject a star from here, you get what we call like gravitational lensing of the orbit. So the stars will be concentrated around the disk, which is where we cannot really see anything with this telescope. So if we were to have a near-infrared version of this, which will peer through the dust of the galaxy, it will allow us to probe within this region that we expect a lot of hypervelocity stars to be. And it will also, in general, allow us to probe into the galactic center. So it will let us know a lot more about the physics that actually brings these stars to be. So let's go, Gaia.
Yeah, what? Last one?
Go on. You were mentioning about the potential information that such stars could give us about the center of the galaxy. Could you elaborate more on what type of information about it?
So that's actually something that I'm working on at the moment, is trying to see what we can learn using the stars from the center of our galaxy. So as you can see here, we have a hard time measuring the center of our galaxy because of the extinction, because of the dust. So getting really nice high-resolution spectra that you can really measure very detailed abundances of different elements, or we even have someone in the audience who measures isotope ratios of this type of stars. And all these things cannot really be measured in the galactic center. So the first measurements will actually come from a star that got ejected from the galactic center, which is this one. So it will tell us about the chemistry, mostly. So what's the abundance of sodium, titanium, vanadium, aluminum. How's the carbon content of the stars here? And that's something that we cannot really measure at the center at the moment.
All right.
let's thank Manuel again.